So here we are, guys. It's Thursday, October 22nd, 2020. We're going to be introducing section 2.2, which is density curves and normal distribution. All right. What is a density curve? This is the definition straight out of the textbook. All right. Density curve. A density curve is a curve that is always on or above the horizontal axis and has an area exactly 1 underneath it. The area of 1 means that it has 100%, it represents 100% of the data. Right? In statistics and probability, we have a range from 0 to 1 for the proportion, and a percentage is just the proportion as a percent. You multiply it by 100 to get a percent. Otherwise, percentages are just decimals, right? And they go from 0 to 1. So 1 represents all of something, right? So we have an area exactly 1. It describes the overall pattern of a distribution. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. Right? We'll look at some extra details here in a moment. Density curves, like distributions, come in many shapes. A density curve is often a good description of the overall pattern of a distribution. So like the lines that we've drawn over distributions to see their shape are very similar to a density curve. A density curve is just drawn a little bit differently to have that specific area of 1 underneath it. Outliers are not described by the curve, and no set of data is exactly described by a density curve. The curve is an approximation that is easy to use and accurate enough for practical use. So it's not going to be perfect, but it will be close enough. And we'll see an example of this next. Right. So we have this distribution here. It's the ITBS vocabulary score. This is a standardized test that is taken in the Midwest. It's for all the 7th graders in Gary, Indiana. The smooth curve shows the overall shape of the distribution. So notice that the curve isn't entirely on top of everything, right? It's cutting off some of the boxes, but it's also above some of the other ones. So kind of the idea you can think of is that it cuts some of them off. So those parts, if I take the cut off parts and put them back inside, it'll fill in the empty gaps that the curve is on top of. So it kind of works out. We see here on this graph A that the proportion of scores less than or equal to 6, right? Cutting off right here. And so these are all shaded. In the actual data set is 0.303 or 30.3%, right? So they took the proportion from each of these histogram bars, right? And that's 30.3% of the total area. On the graph over here, graph B, the proportion of the score is less than or equal to 6, right? So same part of the graph we're looking at. From the density curve is 0.293 or 29.3%. So it's a little bit less, right? We've lost a tiny bit of accuracy. But if you notice, now the shading is just everything under the curve, and we cut off these portions of the histogram. They're not essentially being counted. Now, if we wanted to calculate, like truly calculate the area under the curve from this point over to this point, you would need calculus and a high level of understanding of calculus, right? Because this is not a curve that has a simple equation. And finding area under a curve between 2 points is at least a second semester of calculus in college topic. You will not be asked to do this. You will not be expected to know this. That's just how they get all of these proportions. We use what's called a table of values that allows us to know what proportion of data is between these 2 points under the curve. Right? So we there's a process of stuff we can do to figure out where this data lies, and then we go look at the table and it says, ah, that's the proportion. Okay, so that's how they've figured this out. So, and we'll get into that again kind of next week. When describing a density curve, it is described much the same as a distribution. Measures of center and spread apply to density curves as well as actual sets of observations. Areas under a density curve represent proportions of the total number of observations. Okay, we just saw in our previous example. The median of a density curve is the equal areas point, the point with half the area under the curve to its left and the remaining half of the area to its right. And this makes sense based on how we've looked at median within distributions, right? It's that middle point, half on one side, half on the other side. The mean of a density curve is the balance point, just like in a distribution, the point at which the curve would balance if made of solid material. The mean and median are the same for a symmetric density curve. They both lie at the center of the value. The mean of a skewed curve is pulled away from the median in the direction of the long tail. And again, this is very similar to what we've talked about and we've seen in distributions. When we have a skewed distribution, the mean goes away from the median in the direction of the tail. All right. In a picture, this is kind of what we were just saying. We have a symmetric distribution here and a density curve that's symmetric. The mean and median are both in the same place right down the center. In a skewed density curve, the median is our halfway point. 50% of the data is over here. 50% is on this other side. And the mean is to the right of the median because this is right skewed. The mean gets pulled over this way. And that's just what this is saying down here, what I just said. So this picture is just kind of like a visual representation of that. And a picture of the balance point, right? The mean. The mean is the balance point of the density curve. We can see that if this was a solid piece of metal, so to say, and I put the balance point here, it would tip over. If I put it too far to the left, it's going to tip over. But we have this nice little sweet spot that the weight is evenly distributed. Right? There's an equal amount of weight on the left side as the right side, so we have balance. Normal distributions. Now, this is the point where we're going to start formally defining what a normal distribution is. Right? This is why previously, when we've had something that we've in other classes maybe called approximately normal, I've told you to not use that phrasing and to just say that they're symmetric, because special things must occur for something to be normal as far as statistics is concerned. And so we're going to start talking about what those are. Right? One particularly important class of density curves are called normal curves. The distributions they describe are called normal distributions. All normal have the same overall shape. They are symmetric, single-peaked, meaning unimodal, and bell-shaped, so they taper off on both sides. You can have a roughly symmetric or approximately symmetric distribution that only tapers on one side and doesn't taper on the other side. That it would not be normal. It would just be symmetric. Any specific normal curve is completely described by giving its mean, mu, and its standard deviation, sigma. Right? And again, these are the mean and standard deviation of the population. Okay. And we have examples here. This is a normal curve. with a mean in the middle and a standard deviation to the right. One standard deviation here. Okay. Notice that the one on the left is shorter than the one on the right. Remember, the area must still be 1 under both of these curves. So if it is a more spread out distribution, it's going to be shorter. Right? A less spread out, smaller standard deviation will be a taller curve. Right? You can't have a very tall curve that is also very wide. It doesn't work. All right. The mean is located at the center of the symmetric curve and is the same as the median. Right? So our mean and median are both right here at mu for both. Changing mu, the mean, without changing sigma, standard deviation, moves the normal curve along the horizontal axis without changing its spread. This is the same as what we talked about with adding or subtracting a constant on Tuesday's lesson. Right? It's just going to shift the location of everything, but the shape and spread will stay the same. Those measures of spread will stay the same. The standard deviation, sigma, controls the spread of a normal curve. Curves with larger standard deviations are more spread out. All right. So what we're going to get into next week is basically if we're given the mu and the mu and sigma for a distribution that is normal, we can draw a picture of it without any of the other data. Right? And it's because of other special characteristics we'll get into next week about how many standard deviations will exist within that data. It'll allow us to draw a picture just by spacing things out properly. All right. So that's the entire lesson. The last thing I'm going to do is show you guys the CYU for this week because I had to make an adjustment to it based on the fact that this lesson ends here and not where I previously thought it was going to end. So give me a moment and I will show you that. So stop sharing the screen. There we go. Yeah. And all right. Back to yes. All right. So back on here, here's our week 9 module. We have the 2 discussion boards, which you should be able to do both of those at this point. The CYU here, I had to make an adjustment to. Because I didn't get to quite enough content to do the last question. So question 1 is a percentile question. We have a z-score question for number 2, cumulative relative frequency for question 3. And question 4 was having to do with the normal curve with a mu and sigma. We didn't get to how to draw one of these yet. You could look in the textbook to see how to do this. The page numbers for the entire section that covers like the density curves and normal distribution introduction are listed in the class resources on those pages for today. But this is essentially a bonus question. If you try to do it, you'll get some bonus points. Could make up for getting one of the other ones incorrect. But it has a point value of 0, so that if you do try it, you'll get extra credit points essentially. So you'll get more than the 4 points allotted on this if you try this. So there is that option. And the other questions are multiple choice. So if you do get them wrong, try them again. So I wanted to go over that to make sure you guys understood that I had to change something on there. There is a calculator embedded in here if you need one. So there's that as well.